Alright, I hope you're ready for a brain bender. This is section 4.6, problem number 6, and it's very much a physics problem. Most of these optimization problems are. When read aloud, it says a small frictionless cart is attached to a wall by a spring, so I drew that. Got the cart, it's frictionless, it's attached to a spring. It is pulled 24 centimeters from its rest position, okay, so 24 centimeters, released at time t equals 0, and allowed to go back and forth for 5 seconds. So right off the bat, our interval is going to be from 0 to 5 seconds. That's our interval period of which we're testing. Because the floor is frictionless, if we stretch it 24 centimeters, it will come through 0 to its rest, then it will deflect the other way 24 centimeters and go back to 0, 24, 0, negative 24, 0, 24. If there was friction, that would keep getting smaller until it finally stopped. But because it's frictionless, it'll keep going 24 this way, 24 that way, 24 this way, 24 that way. But beyond that, you can solve this problem without really even needing to know that. Because it says that the equation for position as a function of time is this. It's position, which they're indicating with s, as a function of time. So s of t is equal to 24 cosine of pi t. And the 24 is interesting. It's the same amount that we stretched this thing. So remember, in front of a sinusoid or any sort of trigonometric sine or cosine, that, like for example, if I said sine of 2, okay, so this is 2 sine theta, the 2 in front represents the amplitude. So that means that this thing oscillates between positive 2 and minus 2. And it's a plane wave, so it'll keep doing that on to infinity. But we're only interested between 0 and 5. But anyways, I just wanted to point out the amplitude, 24, represents the amount that the spring was stretched before we let go of it, before we let go of the cart and let the oscillation begin. Now here's the first question. What is the maximum speed? Alright, let's get to it. So, you remember when we want to find a maximum of something, we take the derivative of that something and set it equal to 0? So let's start by taking the derivative of position, s prime of t, which we know as v of t, or velocity. So we're no longer talking about meters, we're talking about meters per second. Or in this case, it's centimeters per second. And so we'll take the derivative of this. The derivative of cosine is negative sine, so we have 24, negative 24 sine of pi t. The chain rule, we have to take the derivative of the inner function. Derivative of pi t with respect to t is pi. So there's our first equation. Velocity as a function of t is negative 24 pi times sine of pi t. Now we're interested in maximum velocity, right? If we were interested in maximum position, we would set the velocity, or s prime of t, equal to 0. And the points we would find would be the maximum and minimum amplitude, which would be when it's deflected 24 centimeters this way, or 24 centimeters that way. Because that would be when x is maximum, right? X is 0 here, it's 24 here, it's negative 24 there. So this would be a maxima and a minima if we set velocity equal to 0 and solve. But we're not interested in maximum displacement. We're asked for max speed, okay? So that's maximum velocity. So we're going to have to go one more derivative deep. So we're going to have to take s prime prime of t, which is equal to v prime of t. So position, the double prime of position is equal to the single derivative of velocity with respect to time, which is equal to what we call acceleration as a function of time. And so let's go ahead and take the derivative of v of t. As you can see here, we'll end up with negative sine is negative cosine, negative 24 cosine of pi t, but we still have the pi here, and when we do the chain rule, we're going to have to multiply by pi again. So we end up with negative 24 pi squared cosine of pi t for our acceleration. Now if we set this equal to 0 and solve for t, we'll find the times at which the max velocity occurs. So let's go ahead and do that. So we're going to set a of t equal to 0, because remember, when our slope is 0, that indicates a maxima or a minima. So we're looking for a maxima. So we'll set this equal to 0, the acceleration. Negative 24 pi squared cosine pi t. beauty here is we can divide by negative 24 pi squared, and that cancels, and this side still remains 0. So we have 0 equals cosine of pi t. And here's a little trick that's going to come in handy. We're going to take the arc cosine of both sides. Arc cosine of both sides. So arc cosine of 0 equals pi t. And this is nice because this isn't a typical cosine, right? This isn't just theta in here. We have pi t. But we can analyze the arc cosine of 0 and then do some more algebra to figure it out. So an arc cosine is saying, instead of giving me an input and I'll give you an output, that's what cosine of something is. Arc cosine is, here's the output, tell me what the input is. So when is the output of cosine 0? Well, we'll look at the standard cosine graph. And it starts at 0, it's at 1. At pi halves, it's at 0, right? And then once again, at 3 pi halves, it's at 0. So we know that arc cosine of 0 is a set that includes pi halves, 3 pi halves, and you can keep going. It goes to 5 pi halves because cosine goes to 0 every odd fraction of halves. And so you can actually write this out as dot, dot, dot. It continues going to 2n plus 1 over 2, or 2n plus 1 pi over 2. And we can test this. If we plug in 0 for n, we end up with 1 pi over 2. That's pi halves. If we plug in 2 for n, or 1 for n, we end up